It's a pleasure to be here. I see a lot of familiar faces. Nevertheless, I have an excuse to give a very high-level description of quantum computing, quantum information science, but I will lurch into some details on the hardware that I have been working with for some time, and that is trapped individual atoms, atomic ions. And here's a picture of a trap that is manufactured at Sandia National Laboratories. That's about a centimeter square. And these atoms basically float above the surface. There are some 96 electrodes here. You can't really see the details. But this is sort of a new technology that is making this platform much easier to use in the laboratory. And because this is a talk on the topic of computing, and especially being here at Argonne, everything I say really should apply to any type of hardware that can be used as a quantum computer, any type of a quantum technology. After all, any computer is independent of its guts. We like to think of a working computer as something that we don't need to know what's inside, or we don't care what's inside. That's the most useful, are the ones that you don't need to know that stuff. Nevertheless, these individual atoms are a very pure system, and I'm going to tell you a little story how to wire them together, and everything I say really should apply to many other platforms, and I think a lot of them are currently being developed here. And it's a very challenging field. The experiments are incredibly hard because they have to be big and quantum, and quantum physics doesn't usually apply to big things. So with that, let me spend a few minutes on a very general tone, motivating the interest in quantum computing, what it is, defining some things. It's true that the field, and maybe even the next few slides, have a little bit of hype there, but bear with me for a little bit. The first piece, which I think is a little overstated, is that Moore's law is ending. Well, a certain aspect of it certainly is ending, and that is that the number of transistors that are packed on a processor cannot continue along this exponential path simply because they're getting too small. And if we fast forward a few decades, according to this exponential law, and these are the number of transistors on popular chipsets over the last few decades, we'll find in 20 years or so that the individual transistors are the size of atoms. And at that point, there is no more miniaturization. Of course, there's going to be very clever things to do that will maybe make an end run around that. And that's why I would be careful saying that computers won't continue to get faster and so forth. But this aspect will certainly stop. And this aspect has been at the heart of the growth of the information era over the last several decades. So this is sort of an interesting issue. We have to think about how we might get around this. Now, in one of my favorite scientific quotes ever, from 1959, Richard Feynman, many of you know this, this lecture he gave at an APS meeting. There's plenty of room at the bottom. He was inspired by the advent of the solid-state transistor. And because it wasn't the vacuum tube, even though it was sort of big and bulky, it was solid state, so it could in principle be shrunk down quite a bit, maybe down to individual atom dimensions. And he even speculates what would happen. He says, well, when we get to that level, it offers completely new opportunities for design. And I mean, 1959, that was a long time ago, and I would say that he really, his vision here was quantum computing, even though it was not known at the time how to make use of it. So in a sense, quantum computing is one possible end run around the demise of Moore's law, if you want. And I think that's an interesting statement. It's very researchy, and quantum computing, it's not a panacea. It's not going to solve everything, but it will solve certain problems that can never, ever be solved using classical computers. And let me describe what that means. Okay, so some definitions, if you haven't heard these terms before. The bits of classical computing in the quantum realm are replaced by quantum bits, or qubits for short. And of course, these can be in a superposition of 0 and 1, a quantum superposition of 0 and 1. And so this is a poor drawing of a single atom that has one electron on it, and that electron is in a superposition of orbits. We're sort of familiar with that concept. The electron can exist in two orbits at the same time. And we write the quantum superposition this way. The state 0 and 1, again, it could be any attribute that you can, that you can define. That there have to be at least 2 levels, and you resolve just these 2 levels. And the alpha and beta are, of course, the weights of how much 0 and 1 there are. And so in quantum mechanics, in straightforward quantum mechanics, we're used to such quantum states as being superpositions of momentum, position, energy, polarization of photons, and so forth. And of course, the confounding part of quantum mechanics, the thing that every student struggles with, is that that part of quantum mechanics is it's a wave theory. There's a wave equation that tells you how alpha and beta change. There are interference effects you can take advantage of. Everything that comes with wave mechanics is included in the evolution of alpha and beta in a quantum state like that. And the confounding thing is when you make a measurement, you of course cannot measure both states at the same time. That has a problem with reality. We need things to be well defined in reality, I guess. I don't want to go down the road of philosophy here, but the way I, at least, am comfortable dealing with quantum mechanics, and probably 99% of you, is that we just think of a different law that we add to the wave equation that says when we make a measurement, it randomly picks one or the other state. And the probability of getting one of those 2 measurements is based on these weights, alpha and beta. Okay? So this is basically quantum mechanics. That's the basic laws of quantum mechanics. Now, what did Feynman mean? What kind of opportunity is this? Well, a hint is that the hint is that a qubit can be in a superposition. It can actually have both states in there. I don't want to say it's storing both states because you can't access both states. But both states have an element of reality in the quantum state, I guess. I'm not sure those words were quite right. Things get interesting when you put multiple qubits together. The simplest number of multiple qubits is exactly 2. And with 2 qubits, something really interesting happens. It should be straightforward that we can allow superpositions like this, where we have 2 qubits. They're in a superposition of 0, 0, and 1, 1 with some prescribed weighting. And this superposition is so-called entangled because the quantum state cannot be separable. You can't factor the left qubit from the right qubit. They're entangled. They have to be considered together. Well, the wave equation is kind of blind to this. It doesn't care. Alpha and beta still follow a wave equation, depending on the system Hamiltonian, the energy of the system. But when you make a measurement, of course, we're going to see that there's going to be perfect correlation, because the only possibilities here are that they're both 0 or they're both 1 upon measurement. So that correlation is perfect. Yet before you make a measurement, each individual qubit is, as far as you know, it's random. If I consider the leftmost qubit, it's 0 or 1 depending on alpha and beta. It's random, but when taken together, they're always the same. So this is rather interesting, and it completely defies all classical laws and classical logic, because if you think about entropy, a quantum pure state has no entropy. I've written it down. There's a pure quantum state like this before measurement has 0 entropy, but when you measure it, when you measure the individual system, it has entropy, it has randomness. So this is an example of the entropy of the bigger system. Sorry, the entropy of the smaller system is bigger than the entropy of the bigger system. So that's one way, if you want, that's one way to say quantum mechanics is not classical. That's one way to think about it. And the idea of entropy is interesting because it connects to information entropy, Shannon's entropy. And this all ties together in the field of quantum information science. I like to think of this entanglement as sort of being a wire between quantum bits without wires, so without physical wires. And as I'll tell you later, as you probably know, for a quantum system to be pure and in a superposition, it has to be incredibly well isolated, meaning that it's nice not to have wires when you don't want them. And there are no wires here, even though there's correlations. So hopefully, anyway, my head's starting to spin. Let me move on. So very quickly, the motivation of quantum computing, I think of it as a story of good news, bad news, and good news. And the first piece of good news is maybe sort of along the lines that Feynman considered. When we have circuits of individual atoms, we can have superposition. So the first piece of good news is that, well, if we put lots of qubits together, well, 3 is not lots, but let's just stick on 3 here, because I don't have enough paper to write down many more than that. With 3 qubits, there are 8 possible states, and in principle, we can store this 8-fold superposition. And I've tried to depict that by this block diagram of the 8 input binary numbers. They all have a grayscale corresponding to their weightings, and you could, in principle, do parallel processing with these 8 inputs. With one turn of the crank, you can compute 8 evaluations of some function. Say it's the log of x or the square root of x. You get 8 outputs. That's great. 8's not so great, but if you go to 300 instead of 8, 2 to the 300 configurations are allowed. And 2 to the 300, this sort of answers the comment I made before. If you need to deal with 2 to the 300 pieces of information, you have to use quantum mechanics because there's not enough space in the universe. There's not enough space. If every atom in the universe is part of a classical computer, or regular computer, it still can't deal with 2 to the 300 inputs. Okay? So every time you add a qubit, you double the size of the system. So the system doesn't have to get too huge before it becomes very interesting. Okay, well that's all the good news, all the nice hype, parallel processing, if you've heard about it. You should always ask the question, well, parallel processing of what? What good is a computer if I can't look at it? And of course, when you look at it, you only get one answer. And worse, you don't know what that answer corresponds to because it's random. So it's just like, it's worse than a classical computer in a way because this output, I have no idea what it means because I don't know what input resulted in that output. Okay? So it's pretty clear that there's nothing new here. Superpositions are interesting, I guess, but we don't know how to use them if we compute, say, a one-to-one function where every input results in a unique output. Well, who said you had to compute a one-to-one function? In fact, I would say that quantum computers will never be good at computing one-to-one functions. And unfortunately, one-to-one functions are probably the majority of things that are going on in this laptop. But there are problems that are not one-to-one. Problems such that the output depends on all the inputs together. You know, like an optimization, the minimum of some very complicated function. That's not one-to-one. What's the minimum? Well, it's one answer. It depends on all the inputs. So David Deutsch is really the fellow who put this together in the 90s. And he showed that, well, there's more to it than just simply measuring. What if we do something to these qubits before we measure? And this is, again, really hard to draw. But I'm trying to, with these red dots, denote interferences between these 8 amplitudes. And there exist problems that can be cast in this form where almost all of the qubits interfere so that the amplitudes go to 0, the weightings go to 0, except for one or a few, a small number. Not all 2 to the n of them, but a small number. And they can carry lots of information on all 2 to the 300 inputs if we have 300 qubits, okay? And then when you make it looks like we made a measurement here, but no measurement has been made yet. But when we do make a measurement, there's no more randomness. So this is an example of a function that's not one-to-one. It's an example of an abstract circuit that a quantum computer is probably pretty good at. Okay? And David Deutsch realized this a long time ago. He came up with some toy algorithms. I say toy algorithms. In fact, I'll show you one or two of them later. They're useless algorithms, but they show that a quantum computer can do something that a classical computer can't. Doesn't mean it's useful. And always remember that. Whenever you read in the newspaper, which is like every week now, that some quantum computer did this and that, remember, it's not useful. We're not there yet. I mean, in 3 years, we won't be there yet. So this is a long haul. We're just putting together qubits. So let me expand on this a little bit. And one of the I would say more murky areas of quantum computing's domain is what I would call optimization. And I think I hinted at it before. Here's a function, a pretty complex and spiky function of just 2 variables. And the question is, what's the minimum? Well, just visually, it's obvious. The minimum is right here. And I can look up x1 and x2 to find that minimum. But if we have a function of lots of variables, of maybe 500 variables, to sample all the configurations in this 500-dimensional space is really hard. And it's exponentially hard. Now, this is an example, if we can somehow get a quantum computer to have interferences find this ground state, this lowest energy state, this minimum state. I use physics terms, energy and ground state, but just the minimum. It could be very useful for lots of problems that hit society, from logistics to finding ground states of complex materials. Pattern recognition, if you have all kinds of data and you're looking for some type of a match with a template. We don't really know how to do this yet, but this seems like the right space for quantum computers to operate. Okay? So a couple examples. One of them, a little more mathematical. This is one such function of bits. Say we have bits x, we have lots of bits here. It's a quadratic function, it's a nonlinear function. Finding the configuration of the inputs that minimizes this nonlinear function is really hard. It's a special example of this. This is actually called QUBO, quadratic unconstrained binary optimization. And it looks a lot like a transverse Ising model. It looks a lot like a magnetic model that we see in physics all the time. So if we can control a bunch of qubits and their interactions to realize this energy function, all we have to do is cool it down. All we have to do. That's really hard. But we have to cool this many-body state down and maybe just look at it and read out its ground state. That could be mapped to interesting problems in society. And I'll say nobody knows exactly how to do this or make it exponentially faster than the heuristics that we know exist classically. But I think we have to build machines and test it on real problems, and maybe we'll get there. It is speculative. Quantum simulations, to me, are a special case of optimization, finding the equilibrium state of a very complex molecule that has all kinds of fermionic interactions that are very hard to calculate. We see this in nuclear physics as well, in QCD. Very hard to calculate what's going on between all these nucleons. And of course, I know there's a lot of work around here interested in materials research, finding new functionalities of exotic materials that we can understand from the ground floor. High TC superconductivity, it's still embarrassing that we don't really have a complete microscopic understanding of it because it's a hard problem. And maybe we can find other applications of that. This, again, I'm not going to claim, I don't think anybody thinks that a quantum computer can solve the traveling salesman problem. But it is an optimization problem. What's the minimum path between a bunch of cities on a grid, on a graph? And it's probably, I think that quantum computers might be an added heuristic to do this. There are technical reasons why we think that the problem is that the gap between the optimal solution and the next optimal solution usually shrinks exponentially small with system size. So that means it'll take exponentially long to cool the system, meaning that you won't get to the ground state, and you might as well just do it classically. So I think that's all true, but I think, again, I think testing real machines with real-world problems is something that we just have to do it. We have to go there. Okay, so that was the very general introduction to the field. And as an experimentalist, I'm much more comfortable playing around with real quantum systems in the laboratory, turning off all the noise and isolating our system. And right now, it's an interesting time. I've been in this field a long time, and in the last two to 4 years, there are 2 technologies now that are being built up. And what I mean by that is they're being engineered in a way that the user doesn't need to know what's inside. And that's really important, and I think it's transferable to any technology. But right now, these 2 technologies are superconducting circuits and trapped atomic ions. They couldn't be more different. One is based on individual atoms, and I'm going to talk much more about this bottom one. Superconducting circuits, these are basically very cold circuits of superconducting loops, Josephson junctions, and they can roughly carry currents in 2 directions. That's the qubit, if you want. There are many different regimes of using a superconducting circuit, but it's been developed by many groups, and now industry is really getting on board here, especially with superconducting circuits. IBM and Google are really leading the way here. And I note that, there is local expertise. David Schuster's lab at U Chicago, he is a kind of a luminary in this field as well. And what I like about these 2 technologies is that they're quite complementary right now. The challenges are completely different. As I'll point out later, we are not worried about our qubit. They're perfect. They're atomic clocks. They will never be improved. The problem, of course, is how do you isolate a single atom? And I'll talk about that in a moment. Superconducting systems, every qubit's a little different because they're man-made, they're fabricated, and that's sort of a nice opportunity here, a place like Argonne, because you are materials experts, and to get materials better and better will help this technology quite a bit. So the qubits are really the problem. The controllers in the microwave, they're not so bad. With the atoms, our qubits are great. The controllers are not so great because they're based on lasers, vacuum chambers, trapping potentials and so forth. So I'll talk a little bit about that. And the big investments in this technology are still rather academic, probably because this is just more exotic. I mean, Intel tells me they're not ready for this kind of, they don't want to invest in lasers and vacuum chambers. Vacuum tubes. Could you imagine Intel doing vacuum tubes? Okay. Okay, so sort of to back up my point that these two technologies are really interesting now is that if we look over time, the performance of the entangling gates that allow you to interfere and make entanglement between qubits has been improving dramatically over the last few decades, and depending on the system, we can hit 99+% fidelity operations. Now, please be aware that this graph is a little bit rosy. It's a lot rosy. All these experiments have optimized the fidelity of a 2-qubit gate. So how many qubits did they use in the experiment? 2, no more. For a real quantum computer, you need lots. And having no crosstalk, by definition, in these experiments makes these numbers quite optimistic. So we have a big challenge in the field to not only maintain this high performance of gates, but also in the face of scaling the system up. When you scale a system up, you're usually going to take a hit in this fidelity. So you have to keep that in mind. Okay, so and again, I point out these two technologies, but everything about quantum computing means that what we learn in these two technologies should be, we should be able to translate everything we learn about that to any technology. And again, this is a speculative field in the long haul. I don't know in 15 years what the leading candidates will be. I hope they're not these. They'll have some role maybe. But I think it's wide open right now on what the future quantum computer with billions of qubits will look like. Okay, so let me now concentrate on my atoms, individual atoms. Again, I say they're perfect because these are atomic clocks. In fact, they're very good atomic clocks. When we make a superposition of two states inside the atom, they can have coherence times that are easily a second. Without any work, we have a second coherence times. They've been measured to be 10 minutes. If you really needed 10 hours of coherence time, we could probably do it. These are atomic clocks. When you build lots of them, they're all exactly the same and very coherent systems. The problem, of course, as I hinted, is isolating them. And that's why we have these traps to do that. Now, another thing to notice is that these traps can operate at room temperature. And the reason is they're in a vacuum chamber, and so there's very little thermal contact with the room. Now, the atoms themselves are laser cooled. So if you want to talk about a temperature, they are cold, but it's not like there's a surface that we have to maintain low temperature with cryogenics. That's not necessary here. Okay, so let's dive into the atom. What makes this atomic qubit? Well, what makes an atomic clock? Microwave atomic clocks are always defined by hyperfine splittings in a particular atom. The atom we choose in our experiments are actually 171 ytterbium, and the reasons will be forthcoming. But ytterbium has a spin 1/2 nucleus, which is actually nice because we can prepare and detect right out of these two so-called clock states. These are the m=0 states that have no magnetic field shift to the lowest order. And so just by storing a superposition in these two ground states, they're separated by 12.6 gigahertz. We can easily have coherence times of a second or even longer, and that's why I've spelled out the frequency splitting all the way to the 1 hertz level. I could give you some more digits if you want, but then it starts to depend on the second order Zeeman shift, the relativistic Doppler shift, all kinds of things that clock people worry about. In ion trap physics, we love atomic clocks, and I started it in Dave Wineland's atomic clock group in Boulder a long time ago. We study systematics like shifts at the 10 to the minus 16 level. That's way better than we need for a qubit. For a qubit, we just need 10 to the minus 9, or even worse than that, and that's just easy to do. So there's the qubit. Sometimes I call it up and down, spin up and down, 1 and 0. And we can store information in an atom using these two levels, but we can also read out the information by gating a laser beam that's on resonance. These atomic ions are optically active and they fluoresce. So when we shine light at a certain color, In ytterbium, it's 369 nanometers, UV. We have to actually write this, know this laser wavelength to about 10 digits. I didn't write them all. But we tuned lasers to hit a resonance. The resonance is only about 20 megahertz wide. That's why you have 9 or 10 digits here. And if the atom was in that state, it will fluoresce strongly, and it will, importantly, come back to where it started. And so it goes up and down. Now, for you atomic physicists in the audience, it can actually leak to these levels, but we can clean that up easily. So just pretend that it goes up and down many, many times. And even though there's one atom, it produces a pretty sizable signal. This is a histogram of a single atom prepared in spin-up. And after a few hundred runs, we've collected the fluorescence after a certain integration time. And we see roughly 30 clicks. We see almost 1 click per microsecond on the detector. And so you can see there's kind of a Poissonian distribution. It's a little broader than that. But this is a very bright signal, and there's an image on a TV camera, a UV-sensitive CCD camera of that single atom. Oh, by the way, that's about a micron across. It's diffraction-limited optics. It has nothing to do with, the atom doesn't look like that. This is just diffraction. The atom is cooled to about a few nanometers in position. It's much smaller than that blob. And the important point of this measurement is that if we prepare the atom in the other state, it's dark. We see nothing. Why? Because that same laser is now 12 gigahertz away from a 20 megahertz line. So it's way off in the wings, and the atom is transparent. We see no fluorescence. See? Nothing. And this is a very good detector. It's an excellent detector because you can, even in a single shot, discriminate between the two states of the qubit. So this is important. In any quantum technology, when you measure it, you don't want to have to average. You want to do it in a single shot with very high fidelity. Quantum systems are isolated. That's why they're good quantum systems, and we're now maximally turning off the isolation here. So being able to gate isolation and perfect readout is very rare in systems. Superconductors do this also. They can gate and read out a current with very low noise and low temperature electronics. Okay, so there's the storage and readout of a single qubit. What about the coherent manipulation of the qubit? What if we want to make a superposition of up plus down? Well, we could do it with microwaves at 12.6 gigahertz. Instead, we do it with lasers also. And the reason is eventually we need to entangle multiple, and we need lasers to do this. I'll get to that in a minute. So we use a technique very common in optical physics, atomic physics, and solid-state optics. And this is called a Raman transition. It's a 2-photon transition. And importantly, each of these 2 laser beams is very far from any resonance. So this is 33 terahertz. Remember, the line width is 20 megahertz. So it's 1 million line widths away. So the atom is sort of like an index of refraction. It's dispersive. And we can drive a 2-photon transition if we can conserve energy, of course, by having these 2 colors of light such that their difference frequency is right near this hyperfine splitting, okay? Well, we actually do this with a pulsed laser, and therefore we have a frequency comb. It's a little technical, but there's all kinds of opportunities here by tuning the comb and so forth that we can drive this transition, and we can scan the beat note detuning and so forth. I promised you I'd tell you why we're using ytterbium. Well, part of it's a spin 1/2 nucleus is really nice for detection and storage. The clock states are easy to access. But I would say the real kicker is that there's an optimum wavelength to do this Raman process. And for ytterbium, the optimal wavelength is 355 nanometers. Why is that important? Well, because you can buy as much power as you want at that wavelength. Like at the NIF facility at Livermore. It's not 355, but it's the same. It's a neodymium. This is a glass laser, but we basically use a vanadate or a YAG laser at 355. It's an industrial laser. And as much as I'm comfortable with playing with lasers and making my homemade lasers, this is a picture of the laser we use. I love this laser because it only has one adjustment. It's the key. You turn it on. That's it. You don't go in there. This laser is used, Coherent makes about 200 of these a year. They're made for lithography, so they have to be reliable for years and years. And so we have 6 or 7 of these. They run for years and years. We don't think about them. That's really important because at least in atomic physics, we want to move away from having to know everything about the laser. We want the laser to be engineered, to be useful, to have users play around with the system without having to even know there's a laser in there. Okay? This is actually a really big deal, and that's why we use ytterbium. Okay, so the next slide is maybe the hardest, but conceptually, I'm going to tell you how we entangle atomic ions. Now, these individual, this is an image of, it's a linear, I didn't talk much about the ion trapping, I just don't have time, but we hold these atoms in free space with electrodes, and it's basically a three-dimensional harmonic trap. It's an ion trap. It doesn't have to be harmonic, but it's a trap. And we make the trap anisotropic. We make it very weak in one dimension so that these Coulomb, these singly charged atoms arrange themselves in a line. Now, if we squeeze the weak axis, eventually this line breaks up into a zigzag transition. There's actually lots of interesting one-component plasma physics here, and I would note that John Schiffer really invented all of this stuff. He knows where the phase transitions are, and there's helices that form and so forth, and he did a lot of the groundbreaking work almost 30 years ago in understanding the structure of these Coulomb crystals. So we all, everybody in the field is, does their work based on his early calculations. These are actually phase transitions. If you squeeze it, they suddenly kink, and then they form a helix. Well, we want to be in the stiff limit where we don't form these kinks. So we have a so-called linear trap of atomic ions. They're separated by several microns, and that means that our UV light can poke an individual atom. It can easily resolve one atom. Well, this is a real image of atoms, so you can clearly see they are resolved. And again, the diffraction-limited spots are maybe a micron or two across. So how do we entangle these atoms? Well, the qubit is stored inside the atom. In a sense, it's sort of like the spin of the atom. It's a pair of hyperfine states. So it's the magnetic dipole of the atom, if you want. You can think of it that way. Now, these qubits are many microns apart. They're miles apart, atomically speaking. They don't interact directly. So there's no way to get them entangled. You'd have to wait forever to get 10 or 100 seconds for them to be entangled by their natural interaction. So we use lasers to push the atoms around in space. Now, while the internal states don't talk to each other directly, the motion certainly does. This is a tightly coupled Coulomb crystal. If we tweak one of them, it's like mass is connected by a spring. If you tweak one of them, they all know about it. And so we're going to use that Coulomb interaction to mediate entanglement of the spin. And here's how it works. It's actually pretty simple and very visual. If we want to entangle these two, we can apply a laser that gives rise to what we call a spin-dependent force. It'll push the atom depending on its qubit state. So for simplicity, if the atom is spin up, it moves up. If it's spin down, it moves down. If you've ever heard of optical tweezers, that's used in all kinds of science, that's exactly what we're doing here. These are two optical tweezers that have a force in this direction. The details, there's atomic physics here, it depends on selection rules and so forth, but this is largely accurate. So if we have two of these atoms, what happens when we apply this spin-dependent force to both of them? Well, if they're both spin up, they move up together. And if they're both spin down, they move down together. And in either case, their Coulomb interaction is unchanged. They move up together, down together, right? But if they're in different states, down up or up down, they're a little bit further apart because they're on this diagonal now. And you can calculate that defect in energy along that diagonal. This delta here is only 10 nanometers or something. But it's a sizable effect to give rise to an effective electric dipole. And this it looks like an electric dipole. We have a charge that's smeared out in two places in general, so it's sort of an electric dipole. And there's a dipole-dipole interaction. It falls off like 1 over r cubed. Okay? Now, if you look at the 4 possibilities of these two qubits, right here, this truth table, we see that the down-down and the up-up state, really nothing happens to them. But the two mixed states, they suffer an energy defect. In quantum mechanics, that means their phase shifts a little bit. And this itself is a nonlinear gate. Why? Because what happens to both qubits is not the product of what happens to the individual qubits. If this were e to the minus 2 I phi right here, that would be a linear gate, no entanglement. But because we can set this phase, for instance, to pi over 2, When you set it to pi over 2, it's just like having a fundamental exclusive OR gate, a controlled NOT gate. So this is basically how we entangle. Now, you're probably thinking, what about all the other ions? When you do this, they're all going to move around. That's true. That's the dirty laundry. You have to keep track of that or do it really fast. If you do this really fast in a time faster than any of the motional frequencies, then you're fine. Right? This is really fast and then back. And then it's just sort of frozen. Everything else is frozen. That's one regime. In practice, we don't do it really fast. We actually do deal with all the modes. And this is what makes it harder to make the system bigger. If you did this with a million ions, it would be a mess. You have to deal with all that motion. Now, in fact, our native operation, it's not exactly this gate. It's similar. It's called an icing gate. And the interaction between the two qubits, it's a little technical here. This basically is the same gate as this in the X basis. And it's just like having an icing interaction between the two spins. And that's the gate we have. So we apply lasers for a certain amount of time on any pair of bits, and we can realize a gate. And this gate is, again, depending on the system, the fidelities are in the 99%. So in the last few years, we've been sort of building up the atomic physics on how to do this. And one of our latest systems, it's rather small with just 5 qubits here. And here we have actually the optical beams. One of them is a big fat beam, comes from one side. You actually have to have counterpropagating Raman beams to have a force. But the interesting Raman beams are the ones that we can focus and individually address any qubit in the string. And this is controlled by a very fancy optical device. It's a multi-channel acousto-optic modulator. We actually have 32 channels. We only have 5 ions, so we don't turn on all 32, but the optics will support 32. And we have RF signals going into these 32 cells, and we can turn on and off any single beam, any pair of beams, all of them at the same time. So you can sort of see, what I like about this figure is that now we have an electrical signal that's going to tell you whether gates go on or not. Electrical engineers love that. So we've removed the atomic physics from it, in a sense. Okay? A lot of engineering goes into making this happen, but in this experiment, we're able to do a gate between any pair of these ions. There's 5 ions. That means there are 10 possible pairs. And we just have to turn on the right 2 beams. And there are other things we have to do. We have to tune those beams in different ways for any of these gates to work. And for the first time, again, 5 qubits is trivial. 2 to the 5th is only 32. You can simulate that on your iPhone. Okay? But what's interesting about this experiment is, at least in my life, for the first time, we've sort of had the full view of this, what we call a quantum stack. The user up at the top is like Feynman. He doesn't want to do any atomic physics. He has a certain task, a certain pattern of gates he wants to do. He says, I want to do these gates. Here we are at the bottom with our linear ion trap and lasers, and we have to fill it in. We have these native icing gates. We have to convert them into textbook gates, controlled NOT gates, and then we can read from the algorithm. So this is what a quantum computer needs to look like. It has to have this full stack. For my whole life, I've been pretty much down here trying to work up here, and then all of a sudden, even though it's just 5 qubits, we're able to do the whole stack. And it's been a real fun exercise, because we can do all kinds of toy algorithms and test them on the system. So I'll give you an example. This is an example of one of these toy algorithms. It's very easy to see. It's called the Bernstein-Vazirani algorithm. And here it is. It's a so-called oracle problem, meaning you're given a black box that does something. How many times do you have to query the black box? Here's what the black box does. It computes a function of n bits, that's x, is an n-bit string. It converts it to a single bit by taking the dot product between every bit of x and every bit of an unknown string, c. And the question is, what is c? I give you the black box. C is encoded in there somehow. What is C? Well, classically, we have to do a single evaluation for every bit of C, right? So you need n evaluations. Quantum mechanically, you can do it just once. You just have to look at that black box once. And of course, the trick is that you've put all the inputs simultaneously in the system. Again, this is a little bit of jargon, but here we have, these are 5 qubits, but we use one of them as a workspace in Ancilla. So this is actually only a 4-qubit algorithm. And H means Hadamard gate, which is it makes a superposition, an equal 0 plus 1 superposition. And so after this step, we actually have all 16 states. Now this is, each of these dots and plus signs, this is called a controlled NOT gate. It flips the target bit depending on the state of the initial bit. And basically the string C is encoded in this pattern of gates. This is 1, 1, 1, 1 for C. If C were 0, 0, 0, 0, there would be no gates here. And then we do this Hadamard gating and then we measure. And in the end, what we're going to measure is C. And this is just one run. Quantum mechanics, you just have to do it once and you get the answer. So we ran this on our system. 16 possible 4-qubit states. There they are. We programmed each of the 16 possible oracles, 16 different circuits, and we measured the output. And it wasn't perfect. Perfect would be 100% on the diagonal here. Every input gives the output. Our gates are about 98, 99%, and there are several of them, so there's some errors. And you can see the errors are sort of crowding up in here. So 90% or something like that. You know, nothing to write home about. It's only 5 qubits. But it's a top-down algorithm, a textbook algorithm. Well, this is completely coincidental. Our friends at IBM also have a 5-qubit machine. It's called the Quantum Experience. They're now evolving up to 16 and 20 and so forth. But about a year and a half ago, they had a 5-qubit machine. This is Jerry Chow, my friends Jerry Chow and Jay Gambetta. And they've really engineered their system. It is autonomous. Many of you probably have run, anybody here has run the Quantum Experience? No? You can run it remotely. It's on the cloud. They had 5 qubits, and so we thought it would be kind of fun to compare algorithms on 2 different hardwares. After all, they're computers. Who cares what the hardwares are? They should both give the same answer. Well, by the way, I didn't mention, it's a superconducting system. So they've engineered that very well. And it gives pretty good results, 80% fidelities overall. Their gates are a little worse than ours. The gate speed is quite a bit faster, actually, but for 5 qubits, speed doesn't matter so much. What is different about the system is that they're not very well connected. Their qubits are on a 2-dimensional grid. This is the unit cell of a square lattice, and they have 1 qubit here connected in a star pattern. Now, here's where some art of computer architecture makes sense. Co-designing your application with your hardware, where would you assign that middle qubit in this algorithm? Of course you would put it here, right? Because this is the one that has to connect to all of them. You wouldn't be very smart if you did anything else. And so that's what you do there, and that's why their connectivity was just fine for this algorithm. What about this algorithm? This is a different oracle called the hidden shift. I won't get into the details, but it's a 4-qubit algorithm, and it's a much more complicated, it's basically instead of finding that hidden string, you're finding the shift between 2 identical functions. The same function just with an unknown shift. Classically, actually, it takes exponentially many trials to find out what that shift is. Quantum mechanically, just once. The function is nonlinear, and programming a particular shift requires lots of connectivity. And if you look at the 2 systems, you see a huge difference. And this is an architectural difference. It's because the qubits in the superconducting system are not very well connected. You can't do gates like this without swapping information around a lot, and that gives you lots of errors. Okay? So the lesson here is not that ions, trapped ions, are better than superconductors. I'd say everybody knows that. All right, supposed to get a laughter there, but they're different. Remember, the clock speed is 1,000 times slower with the ions, but they're better connected. So that actually makes up for the clock speed. So the lesson here is if you want to do something with a quantum computer, you better know how your qubits are connected. You better dive into the hardware. And we're going to see this in this field for the next 10 years. In all effective quantum computing systems, the software and hardware people are going to have to interact really tightly. Mighty atoms. So I put this slide here because this is a really ugly looking system. It looks like a university system. I mean, these blade traps, they even look like, they're taped together. They're spout welded. This is not something you might consider scalable. It's very hard to scale this particular type trap. But with this system of just 5 qubits, it's been an interesting year or two. We've been approached by people from everywhere. They want to run their system on 5 qubits. They're not going to learn anything with 5 qubits, but they still want to run it because when we have 50 qubits, it gets interesting. When they have 500 qubits, it gets real interesting. So we're doing all kinds of fun experiments. One of them in particular, I really don't have time to talk about it, but we've expanded to 7 qubits, and we're basically detecting whether a given 3-qubit operation scrambles. If you ever heard that term before, it actually has to do with information in black holes, believe it or not. And if you have 3 qubits, they can entangle but not scramble. You know, scrambling is it's basically information that covers the entire space, the Hilbert space of the qubits. And we're basically applying this circuit as a litmus test for a given unitary. Does it scramble or not? And you know, here are 2 example circuits of a 3-qubit unitary. One of them scrambles, one of them doesn't. I forget which one does. I mean, it's a very subtle concept. But we're connecting with people in astrophysics. It's kind of fun to think about, you know, what happens to correlation between entangled pairs that you have and one went in the black hole, and is the Hawking radiation correlated at all with the qubit that you had behind? Interesting questions there. Now, as I pointed out, we need to not only push the number of gates up, that is the error per gate, but we also need to push the number of qubits up at the same time. It's sort of easy to work along that direction or that direction. I mean, I can give you 1,000,000 qubits that have terrible gates, or I can give you 2 qubits that have amazing gates. It's doing both at the same time that's really hard. And there's sort of a bellwether at 45 or 50 qubits. You've probably heard the term quantum supremacy. With 50 qubits, you can't simulate what's going to happen generally. And so having even a 50-qubit machine is of some interest. And in fact, we do have ion traps that have broken this threshold, but they don't have full control over the qubits. So it's very similar to the system I showed you before, except we don't have individual beams. We hit all of 50 or 53 qubits. 53 is the number we have most so far. We hit it with a big fat beam, and we have this global icing interaction. It's a transverse icing model. And again, I just don't have time to go through the details. These are 53 ions, and we're basically studying, as a function of B over J, the transverse field versus the interactions, we're studying sort of the average domain size of this magnetically ordered system. And we see actually, I'm going way too fast here, we see a phase transition in the mean of the largest domain size, this kink, that we could not calculate. The system's, I don't want to say it's a useful material that this thing is modeling. It's a long-range icing interaction. But we can't calculate where that kink is beforehand. We had to measure it. And it's an example of something that we hope to apply control to a system this big. But the trapped ion system, I mean, this is sort of the biggest trapped ion experiment that has really shown measurements of individual qubits. And clearly, there's a case to be made to scale up the technology we have for individual gates to this much bigger system. Well, my feeling is that whatever the quantum computing platform, it's going to be modular, for the simple reason that a big quantum system is no longer quantum. So you can't just simply make your square lattice grid as big as you want. Eventually, it's going to hit the sides of your vacuum chamber, or it's going to burst outside of the dilution refrigerator or the lab. So you have to stop. And then think about bridging to another maybe square lattice chip over here, or another collection of ions and so forth. And so this is clearly a plot of airline routes throughout the world, and clearly the airline maps are modular. You can't fly from anywhere to anywhere. That would be economically ridiculous. And I think quantum computers are going to also evolve in that way. It's physically ridiculous to imagine controlling every one of 1 billion qubits individually. You have to sacrifice connectivity in order to make the system bigger, just like a multi-core processor does. We don't make processors as big as this stage. We wire together 512 small processors to make the system more powerful. And so I would say, depending on the physics of your system, this is sort of an economic diagram. How much does it cost per qubit versus the number of qubits in your system? And I would argue that pretty much any physical system I can think of will have a curve. Maybe it doesn't look exactly like this, but it starts out at some finite cost. 1 is not interesting, because you can't do entanglement. 2, just to get on the table, to entangle them is some expense. But to go to 3 is actually significantly more, because there's crosstalk you have to do and so forth. But there's probably going to be a sweet spot. I mean, if you have 40 qubits, why not have 41, right? And it's not going to, how could that cost anything? But the interesting thing is there's going to be at some point where the noise just overtakes you. And this is not fundamental, but it's going to be in practice. And hopefully this gets shifted more and more to the right as we grow better materials and get better at our experiments. But in any technology, including trapped ions and superconductors, right now, I would say this knee is going to be in the range 50 to 200. And with ions, it has to do with this complicated motion. Right? There's too many degrees of freedom. You don't want to deal with them. So in a single module, you probably want to stop at this point. If I plot lines of constant dollars, this is, again, 2 to the order of magnitude, maybe. You clearly are not going to spend more than 100 million here, right? Because you're not going to get many more qubits by doing it. The noise just gets too insane. So this sort of implies that you have a modular architecture. You have to have a modular architecture. It's not a theorem, but I think we're going to see that playing out in practice. Well, with trapped ions, we actually have an opportunity. I didn't talk about this much at all, but we can also move quantum information through photons, individual photons that are emitted from these ions. And this is sort of a concept picture of how you might scale up a bunch of modules. Maybe each of these traps contains 50 ions. And if we can stamp them out, we can think about having a subset of them connect to single photons. What's in here? Everything to the right of here is classical optics. This is a sort of like an old telephone operator. It takes any 2 input fibers and maps them onto any 2 output fibers. Here we have fiber beam splitters and then a CCD camera at the end. Let me kind of get in the background of what's behind this. The idea is this is an entangler, and it will sacrifice and detect the photons in order to entangle atoms that are really far apart. It's a different way of entangling. And again, it's not unique to ions. I mean, there's work here involving quantum dots, all kinds of plasmonic devices I saw this morning that are very exciting to make this solid state. We would love to move this to the solid state, but atoms are standards. You don't have to worry about the photons being different, and that's why right now the state of the art is with atomic systems. So here's our ytterbium energy levels again. Now we're going to map a superposition of spin onto one of polarization of a photon. And we do this by exciting resonantly to this p state. Now this is not a good place to store quantum information because this is going to radiate in a few nanoseconds. But when it does, it can decay via many paths. There's a selection rule. It can't go here. And in fact, it won't go where it started if we collect the light along certain directions. So we end up with the photon either emits with this polarization or that polarization, and the atom is now in 2 different states. And technically, we can move these states around. We do it with microwaves. But in the end, what happens is we have sort of an entanglement between that single photon's polarization and our qubit and our memory, our atomic clock memory. Now, it's only weakly entangled because this photon, maybe we didn't get it. Maybe the detector didn't click. Maybe the photon didn't get into the fiber. All kinds of losses happen. In fact, the losses are pretty severe. The probability of success is less than 1%, and that's actually pretty good. That's the state of the art. And if you look at the rates aren't super fast. We can generate these atom-photon entanglers not very fast, but again, the fidelities are very high. And this by itself is not useful. We need to somehow connect it to another node, and we do this this is a known protocol now, we do this by doubling the system. I should say squaring the system. Now we have to get lucky twice, and getting lucky means 0.5% squared. So very rare, 0.5% squared. And I won't get into the details, but these photons, when they interfere on a beam splitter, we can detect certain correlations that destroy the photons but leave entanglement behind in the spins. What's important is these photons are identical. And because they come from the same atom, same atomic clock, they are identical. We never worry about that. They're identical. They do have to be mode matched on the beam splitter. There's some alignment there. And if you want slow, this is slow. Here's the current state of the art in generating remote entanglement. It's only a few per second. So if you want to think about building a big quantum computer with a clock speed of 10 hertz, nobody's going to get too excited. But the important point is that actually we're at 10 hertz now, but only 5 or 8 years ago we were at 1 millihertz. Click every 10 minutes. That was painful. So now we can take data at least, but we need a few more orders of magnitude, maybe by using integrated optics. I mean, there's a lot of work here in that direction. This is where solid state is going to play a role. It's going to make these rates much faster. I just see it happening. I'm just about done here, sorry, but a quick picture of the lab. This is an old picture of two vacuum chambers. Two vacuum chambers that each hold a single atom, and underneath the black, behind the black door here is where we entangle the atoms based on their photons. Black, obviously, because we don't want dark counts. In this experiment, we actually teleported, I'll say it, try to say it with a straight face. We teleported a single atom from there to there, a meter away. And people get really mad when I say it that way, but we have the same atom over here, and its personality is the state. So to be more accurate, I should say, we teleported the quantum information contained in this atom to that atom. It's only a qubit, so it's not a big deal. So Charlie Bennett invented the term quantum teleportation from IBM. It's kind of unfortunate, but it actually is, it's interesting because it is the being of the atom. It's its state. We've distilled it down to just a single qubit. And using the same protocol I talked about, we can basically move that information, A and B, from here to here without betraying it, without measuring it. We could also move it by just brute force moving the whole vacuum chamber over, hopefully quickly before magnetic noise takes over. But we can do it using this probabilistic protocol as well. And that's a good way to move information around in this networked quantum computer we're thinking about. The bad news with ions, this is maybe a typical AMO lab, and this is actually the same lab here. The vacuum chambers are just right there. All that other crap is lasers and controllers, 9 digits of stabilization, and that's really the problem. I mean, that does not look like a system where the user doesn't need to know anything about lasers. So that's a big problem. It's a big challenge in our field. We have these great qubits. Boy, I wish we could control them. So I always show this picture alongside this one, which is the old vacuum tube ENIAC, where people had to maintain the vacuum tubes constantly, very unreliable. Well, the good news is that we've been working with IARPA and the agency IARPA and a few industrial partners to engineer that system. So actually, everything you see here, believe it or not, everything you see here has been condensed to more than a factor of 10 in volume, more than a factor of 10 in linear dimension, down to this, it's about a cubic meter. It's not even closed up. We're making things small, not just to make them small, but when they're small and autonomous, they will perform better. And the user can, again, get access to it without worrying. There are also cables from all these bulkheads over to here that are drawn. These blue cables, there's 32 of them. You know what those are for? It's to control 32 individual beams. So inside this vacuum chamber behind the black wall here, we have a Sandia chip trap with lots of ions that we can store in there, and we hope to control up to 32 qubits in that system. If this looks like a company activity, it certainly is, and the reason is we're definitely pushing against the limits of what we can do at a university here. IARPA, again, has funded us to an extent where we can have research scientists and have strong industrial partners, but it's not sustainable. I mean, I don't want to spend my life every month writing grants and monthly reports. So we do have a startup company, it's called IonQ, that will build based on this template. It's venture capital funded, which has its own issues, but our partners are very long-term investors. They want to see a path to something in the 5 to 10 year time frame. I'd love the NSF to say that. Anybody from NSF here? Okay. So it's an opportunity, and we're taking it. We're going to engineer the system. And we have 20 people now. We're probably going to have 40 by the end of 2018. It's a big operation right off campus. And this is an artist's rendition of their module. It's not tiny. There's no refrigerator here. It's all room temperature, but it's big with the optical controllers and so forth. So again, so the overall picture is that I've talked quite a bit about ions, but again, anything I talk about, I think it needs to be transferable to any technology. And right now, ions and superconductors are the ones that have all this control with small numbers of qubits, but there's a whole host of materials, other quantum systems that we look forward to using in the future to build real devices and solve some of society's very hardest problems. My colleague Bill Phillips at NIST in Maryland is fond of saying that, it's useful to keep this in mind when you're building a quantum computer. He says that a quantum computer differs more from a classical computer than a classical computer differs from an abacus. And that's true because, I mean, these look a lot different. classical computer and an abacus, but they're basically the same Turing machine, the same physical universal principles of classical computing. These two things are different. They're totally different rules. And I would say to those that are married to a particular quantum computing architecture, especially silicon, why on earth would a quantum computer look anything like silicon? It's just one example. I think we need to, I mean, Argonne is beautifully set up to explore all kinds of different materials, from atomic systems to solid state, to quantum dot emitters, to silicon, and other dopants, other semiconductors. And I think because of industry's investment over the last few years, I think we're going to very soon see just a golden era of discovery in quantum computing over the next decade or so. So again, this is a picture of my group. We're just inside the Washington Beltway. And speaking of the Beltway and Capitol, many of you know that that Congress is on the scene, and they want to fill this gap between university and industrial research to get a quantum workforce out there. And I've been very active on the Hill, kind of unwittingly, promoting the idea of a national quantum initiative. And I think places like Argonne or DoD labs, industry and academics, but especially those in the middle, like this laboratory right here, will play an especially crucial role to keep the US in front in this field. And it's a big deal because China and Europe, they're all across the world, they're going gangbusters with initiatives like this. So, okay, thanks for your attention.
Thank you very much, Dr. Monroe. Questions, please.
Fascinating talk. But one thing you mentioned, maybe I didn't, and maybe you answered, but I didn't hear it. Gates, you said, you seem to be happy by Gates working better than 90% of the time. Is that something that's trivially easy to overcome? Because I imagine you need much better than that.
Yeah, okay, so you bring up an interesting topic, and it's not like I forget to bring this up, but 99% gate would imply that you can do 100 operations. It depends how the errors accumulate. But let's say it's worst case and you could do 100 operations. That's not very interesting. You need to do many more than that. In fact, there's something I didn't talk about, the topic of quantum error correction. Now, classically, we have errors in our computers, and in the early days, there were parity checks and so forth. A little bit of redundancy in coding can allow you to square the errors. And if the errors are 10 to the minus 8, you go to 10 to the minus 16, that's great. It turns out the same formalism applies to quantum. I mean, this was actually a big deal when it was shown that you can do quantum error correction. The problem is, to square the error, the overhead is enormous. You might need 10,000 qubits to store one effective good qubit. So the overhead is insane. Some would argue that to do full quantum computing, you have to do it fault tolerantly, and you can't disagree with that. But we're not even close to touching that yet. I don't think in the next 10 years we'll be close to touching it. So is 90% good enough? No. Is 99% good enough for something interesting? No. 99.9%? I don't know. I'm hoping that pre-error correction, there's something interesting that will happen, maybe in the optimization space of 200 qubits, 99.9% fidelities. You certainly can't simulate that device classically. That doesn't mean it's interesting. But I am of the opinion that if we'll never get to 1 billion qubits and parts per million errors if we don't try to build a few hundred qubit machines. So it's an awkward position to be in, I'll admit. There's no killer app with a few hundred qubits, but yeah, good point. I think Linda had a question up front.
Great talk. What's the fundamental reason for back here? Why do the trapped ions have to stay in a line? Why can't I have maybe 2 lines of trapped ions and apply a laser pulse to both lines and sort of have some entanglement not in one dimension?
So the question has to do with the dimensionality here. Indeed, you can make 2D trap arrays. There's a technical reason that's a little hard, and that is how to say this. The only way to make a two-dimensional grid of ions, one way is the so-called penning trap. That means that they're all rotating in rigid body rotation, so you have to deal with that. The group, John Bollinger and Dave Wineland at NIST, have kind of pioneered that, and they can do certain global things with a few hundred qubits. But more interesting is having a chip that has individual electrodes, one per ion, and then you can sort of pattern your ions any way you want. The problem is the ions have to be away from the surface to be isolated from them by maybe 30 microns, and that means the ions are separated by 30 microns. These ions are only separated by a couple of microns. If you multiply that by 10, in some cases, the interaction goes down by 10 cubed, the dipole-dipole interaction. It just becomes very slow. And so people are kind of thinking about that, but I think I'm very hopeful that we can go to 50 or 100 in a single line, at least, and have full control of everything. And then, my approach is more of a modular thing, but I think until we get there, the two-dimensional systems are a little more researchy. But when we get there and we say, okay, we can't do more than 50, then I think we should think about higher dimensions. 3D is really hard to hold. Anyway, that's a real problem with these atomic systems. But good question, thanks.
Yeah, actually, my question was the same as John's, but just to follow up, I think in your talk you were, and that had to do with why is 99% fidelity good enough or whatever, but in your talk you had a comparison between the trapped ions and the superconducting qubits, and it seemed to show that the trapped ions were much better at error correction than were the superconducting circuits, and maybe you can explain a little bit why that is.
Did I say about error correction or just error rates?
Just error rates,
Yeah.
error rates.
Well, again, the superconducting circuits are getting better and better, but there is surface charge noise on these superconducting circuits that can affect the qubit state. That's actually not so bad. They're little trapped two-level systems that give 1/f noise. The real problem, though, is when you make this circuit bigger, each of the qubits has a different frequency. At IBM, they probably do the best at engineering their individual qubits, and they still have a spread of 5%. They can't, if they target two frequencies, they will be somewhere in a 5% window. And so when you throw 50 of them on a chip, you're sort of, the yield will be low, but when you get your perfect one, it will have different frequencies, and those frequencies drift. If you cool down the fridge and come back, their frequencies will be different. And so it's not exactly understood how that will scale. It is improving. But then there's readout. When you read out the quantum, the Josephson junction in terms of a current, there is noise on that. The more there are, the more noise and the more crosstalk there is. So you have to fold that measurement noise into the effective error rate of the qubits. So it's a different challenge there. And it's interesting that we're both right around 99% with 10 qubits or something like that. Totally different error sources. With ions, the errors are 100% the lasers. The errors are not in the qubits. When we turn the lasers off, the qubits sit there forever. Well, forever, much longer than any of the relevant times. But when we entangle them, we're pushing them around with a force. There's noise on the laser. There's beam pointing noise, all that stuff. I'm confident we can engineer down. It's all classical. But nobody's really done it, and it's the big challenge. And it's interesting that the noise at the end is sort of the same on both systems, even though they're from totally different sources.